Okay, so this is the low voltage op-amp setup. We have a number of things in this circuit. It is a non-inverting amplifier. Here are our two resistors that form the gain of the non-inverting amplifier. My output is being taken from here. But you'll notice that the other resistor, these are the two resistors at the back that set the gain, instead of going to ground, it's going down over here, and it's going to the output of this op-amp. This is set in unity gain configuration, and it's amplifying with a gain of 1 this voltage divider. This voltage divider uses two 10 megohm resistors to divide the power supply in half to get 2.5 volts. Notice I have a capacitor here to filter out noise which is easily picked up by this high impedance. I was getting a pretty large 60 Hertz power supply signal on mine, which drove me crazy for a while. So out of here is coming a 2.5 volt signal, halfway between the power supplies. That's my new reference or ground. That reference is then being used by this amplifier. So my input signal, which is coming in over here, going through this capacitor, has to then be moved to that reference. So I have a 10 megohm resistor here, and 10 megohm resistor here, hook up to the output of that capacitor, that puts the 2.5 volts on to my input signal, so that it's my input plus 2.5. It goes into the amplifier and then gets amplified and comes out. And so I'm expecting to see an amplified version of my input, but with a 2.5 volt offset coming out. Let's go look and see what's on the oscilloscope. So here I have it set up in sweep mode, and just for your own information, I have this thing set up with the high Z load so that it really is 300 millivolts out. Interestingly, it's hard to measure this directly on the circuit because we have 10 megohm resistor loads, and when you put the scope on, that's another 10 megohm, and it actually changes what's going into the amplifier a little bit. So hooking the scope up to the inputs can cause trouble here. So here's my output, and what I see is if I switch to a quick measure, I can see that about a 2.8 volt signal coming out, which is about a gain of 10. I have actually 820K and 100K as my resistors, so I should get about 8.2 plus 1, which is 9.2. And I'm getting close to that out. If I put the cursors back on, and I set the cursor values to 5 volts, and 0 to my power supplies, I can see that indeed my output is halfway between the power supplies. The other trace on there is the output of the amplifier that's generating the 2.5 volt signal. And it's good to look at that because a lot of the problems I've had with building this are when noise gets onto that output and causes trouble. For example, if I pull off this capacitor over here, this capacitor here, if I pull it off, with a bit of luck, I'll pick up, yep, now I'm picking up 60 Hertz on that, and look what it did to my output waveform. It looks like total garbage. If I look really close at the output of the amplifier and set the scope up just right, I can see it's 60 Hertz. But all I have to do is put in, this is a 0.1 microfarad. So this is a form of decoupling, 0.1 microfarad, and it comes back and looks clean. The other problem I've had with this amplifier, this is a very low voltage and low power amplifier. It's not designed to drive huge loads, so that's why I have an 820 kilo ohm feedback resistor. If I put other resistors in, I get crossover distortion like we saw with CMOS output stages, and these actually have CMOS output stages. from driving too much current. So be careful about the size of your output loads. In the data sheet, they do talk about some circuits that will let it drive lower loads, but it will up the power consumption. So if you're trying to get low power consumption, stick with this. My output resistance here, you can see these both have yellow in that last band, so it's 8 to 10 to the 4, 800, and I think that's right, 920K and 100K resistors. Okay, so that's the single supply op amp.